All right, so the kind of the last thing that I wanted to talk about with this, and we can extend and talk about other things if folks are interested, but the thing that I always think is like an important, at least analytic result to get to is the calculation of the static structure factor. All right, so the thing that we want to get is an expression for S of K for polymer solutions. And so this is because this is something that can be measured experimentally. And thanks to some important results from like classical density functional theory, it can be related to free energies very cleanly. Well, maybe cleanly is overstating it a bit, but it can be related to free energies. I sort of debated on how much of the DFT part of this I wanted to go through to like build out that analogy. But I guess let's talk through the structure factor first. I mean, formally, this thing is defined as the Fourier transform of the particle densities. Right, so it's a 2-point density correlation function. Right, so it's analyzing correlations in the density of the whatever you have at location R and simultaneously at R prime. And then you have to subtract off some the background of just like the average densities at the two locations. And there's a very rich amount of thermodynamic information that is buried in S of K. And all of this stuff that's on the right-hand side, you can think of that as just being related to the radial distribution function G of R. That's very commonly calculated in simulations. And S of K is the thing that can be measured experimentally that kind of gives you the same information. The big difference is that it's measured in reciprocal space. So it's basically measuring the Fourier transform of G of R. And just to kind of highlight what's on the right-hand side, these are equilibrium averages of the density, right? There's the second moment of the density where we have density at two different locations, and then we subtract off the product of the first moments. And so it's sort of like a fluctuation formula, but it's for a spatially varying function. And that the Fourier transform of that is really what we're ultimately after. And I guess if we wanted to build out the connection to density functional theory, the whole idea from DFT, classical density functional theory, is that you can write an expression for the free energy of the system as a functional of the densities. And the whole DFT framework is basically a method for coming up with this relationship. And it's tedious and very formal. But what you can show is that the quadratic coefficient, if you do a Taylor series expansions, so if you do a Taylor series functional expansion, the quadratic coefficient is proportional to 1 over this stuff. And so, all right, so if you do a functional expansion, so like the functional version of a Taylor series expansion, the quadratic coefficient that goes as 1 over, really, we typically would just write it as 1 over S of K because you can write, it's most convenient to write these coefficients in Fourier space again. And so it goes as 1 over S of K. And so then because that's the quadratic coefficient, that's how much you need to be able to predict when a homogeneous phase becomes unstable. Right? Because that's when you can have when the sign of that quadratic coefficient changes, that's when you get free energy that will decrease as a function of density. And so you will get something that will become inhomogeneous. And then the length scale on where you have that inhomogeneity depends on the K where that happens. Right. So if 1 over S of K goes to 0 as K goes to 0 from the right or from the positive side, that means that you're getting macrophase separation. Right. So that's why in a static structure factor that you would measure, seeing that low Q or low K upturn is one of the signatures of macrophase separation. It just gives macrophase separation. Phase separation. So that would be like a binary polymer blend, phase separating A from B. And the cool thing that you can get out of doing everything this way, where we retain some of the spatially varying stuff, is that if 1 over S of K goes to 0 for finite K, then that's indicative of microphase separation, right? So that means phase separation on finite length scales. And so that's like what block copolymers do. So if 1 over S of K is going to 0, like that's the interesting limit to look at, that means that S of K itself has a pole, right? So it'll diverge as K goes to 0, or it will diverge at finite K. And so that's why being able to compute S of K can be very important, because then it lets you predict kind of a rich variety of behaviors, right? You can see macrophase separation, you can see microphase separation. And with these polymer models that we have, you can start putting these things together in different ways, and then analytically study what type of phase behavior you will get and what limits. And so that's kind of the last thing that I wanted to go through as like the main topic and sort of motivation for it. And I guess, but first, are there any questions about like the basic premise here? Like why we would care about S of K? I didn't want to go through all the DFT stuff to make this a little more formal, but Hansen and McDonald chapter 3 is where that's somewhat laid out as clearly as they can make it. But it's not the clearest thing ever. Anyway. So, and so then really in coming back to like the field theory stuff and everything that we've been doing, what we want is something like the right-hand side of this guy. And really like, this is the guy that we now need, right? We'd be able to compute the second moment of densities. Right, so we want the spatial correlation function of the densities, or the 2-point correlation function of the densities. And being able to do that in general is tricky. Like doing it for just the homopolymer in an implicit solvent, that's pretty easy. But then even like extending that to block copolymers gets very tricky very quickly. And so that's why I wanted to go through this. And the thing I was going to share my computer up. Um, So this goes back to, so I'm scrolling through my field theory papers. Forget if I showed this on one of the first lectures, but this is the kind of the classic first application of this. So I guess one step back is that the nice thing about DFT is that it lets you do this functional expansion up to arbitrary order. We're only dealing with like the quadratic term here, and that's the only one that I know how to calculate reliably. But in general, with DFT, you can go out to higher order stuff. And that's kind of what this, so there's this famous polymer physicist chemist in France, Ludwig Leibler. He's still active today, I believe. But he had this kind of seminal paper back in, I guess, 1979. So the year that I was born. So it is a super old paper. But it's also the second most cited paper in macromolecules, from what I understand. And it's lays out a theory for microphase separation in block copolymers by showing exactly this. Right, it shows this, and then he actually goes out to the 4th order terms in this expansion to be able to like predict what the actual phases are that it forms. And so it's not a light read. So I'll just click through it a little bit. You'll see many, many many equations go by. I think it has on the order of 100, 150 equations in it, something like that. But you see all these expansion coefficients and all the stuff that he's worked out. It shows a decent amount of the work. I've never actually gone through it to understand it super well, but it's it's here if you want to work on it. And that's just to show that it's not easy to do this stuff. And then the other thing is, like, when I was trying to come up with my own way to do it, I also want to show like how non-trivial this can be. So this is a small part of the notes that I have of my work trying to just work on field theory stuff in general. And I'm just going to call your attention to the different ones that are labeled die block S of K. And so this is the first one that was made back in 2019. And that's when there are, pencil and paper physical copies of this where I've tried it before this. Then there's 2.0. And just to be clear, like, these are not just small notebooks, right? These go on for quite a bit of me trying stuff and not being able to get it to work and not get the expressions that I expected. And then there's 3.0. What's the date on this one? It's still 2019. 4. Oh, we're up to 2022 now. Just trying it on my whiteboard. It's getting closer at this point. And then number 5 is the one where I finally got everything to work. And this is the highlights of what I will show probably next time. But, just to make the point that this stuff takes some trial and error and some practice. All right, so what's the actual reliable way of getting the structure factor? Let's dive into that. Okay. All right, so the thing that we need to be able to do this is, again, the sort of key thing that we are after is this guy. Like, if we can calculate that second moment, then anything else is going to be like getting the first moments will be straightforward because we'll need those along the way. And we're not too concerned about that. So we need a reliable method of getting at this. And you can do it from the types of field theories that we've derived so far, but it tends to be even more subtle and tricky and annoying than what I'm going to show you. And so it turns out that it's a lot more convenient to start from a different starting point for the field theory. And so what I want to do is show the other way of deriving one of these field theories. And so there's another form of field theory and we use these Gaussian functional integrals to derive the field theories that we've worked with so far. Everything was, we just used these Gaussian functionals. We were restricted to two-body interactions. And we called those Hubbard-Stratanovich transformations based on the folks that originally did it. And this other flavor uses something that's called, I've been told that this is called the, sure I get my spelling right, Fadeev-Popov transform, which again is another thing that has its origins in quantum mechanics, but it's, and this language is actually not super commonly used. This woman that said, I think in Mainz, Friederike Schmidt is the one that told me that it goes by this name. But the basic idea is that instead of using Gaussian functional integrals to get rid of the densities and replace them with just potential fields, we're going to derive models that have explicit density fields in them, but they're going to be continuous things that we can differentiate instead of like rho hat. Okay, and the way that we're going to introduce them is using Dirac delta functions, sort of like how we enforced incompressibility. All right, so we're going to go back to the Edwards model just as a demonstration of this. And so remember, this was the Gaussian chain homopolymer in an implicit solvent. Right, so this was our bonding potential beta U naught. This was sum over all chains, sum over monomers. It was 3 over 2 b squared RJS +1 minus RJS squared, right? That was our bonding potential. And then we had the non-bonded interaction. That was 1 U naught over 2 dr microscopic density squared, and then minus some self-interaction term that we just sort of threw in the prefactor and forgot about. And just like with Hubbard-Stojanovich, we're going to start from the with the partition function. And so we'll have our Z0, indistinguishability, thermal de Broglie stuff. Then we'll have our integral over all coordinates, little n, big N, and I'm actually just going to jump straight to being sloppy about the distinction between n and n plus 1, because we've seen that that kind of goes away in the analytic stuff anyway. Then we'll have e to the minus beta 0 times e to the minus beta u1. All right, so just normal particle partition function. And then the thing that we're going to do is multiply this guy by a really complicated way of writing 1. So we're going to say d rho, then a Dirac delta functional, rho of r minus rho hat of r. And again, I'll remind you that rho hat of r, right, this is the microscopic particle density. This is the thing that's the sum of delta functions. And then we have our rho. That is our continuous field, right? That's something that's differentiable. Right? And because this is an integral over rho, so this is, you can think of this as being like an integral of over x of a delta function of x, right? That's just 1. So we're just multiplying by unity when we do this. So this, and then the next trick that we're going to play is the usual game where now we can write this delta function, functional, as an exponential, right? And this is what we used when we did the incompressibility constraint. We just wrote this as a functional integral over a field with an imaginary unit times the argument of the exponential, or the argument of the delta function. Right? And so then that will be the same kind of trick that will let us turn this into a from particles to field theory. Okay. So what do we get when we do this? I guess the first thing that we can say is that if you have some sort of general function of rho hat times a delta functional, rho of minus rho of r, you take this integral. This is because this delta function constrains these two things to be equal everywhere, then you can also say that this is equal to the integral d rho f of rho without the hat times delta rho hat of r minus rho of r. Okay. And again, I realize the notation kind of sucks that you have to be very careful and think about the difference between the thing with the hat and the thing that doesn't have the hat. This is just, I don't know of a better way to convey this at the moment. But the thing that this lets you do is in the non-bonded energy, you can get rid of the microscopic particle density, the thing that would be the n squared sum over terms, and replace it with this continuous density field. Okay. Right. And then, okay, and so then we can write the so we can use the exponential form of the delta function. this is equal to an integral over a field, dw, e to the I r w of r rho of r minus rho hat of r. And I guess before I erase the structure factor bit that's up here, I'll just say that since we we have this delta function that's going to enforce this constraint for us of the equality between the particle density and this field density, we can get S of k equivalently by just getting the second moment of rho without the hats at r and r prime. Right, so that's the problem is shifted ever so slightly, but in an important way. Okay, so plug into Z. So this is our partition function. It's going to be momentarily a little messy. So we still have our prefactor, n factorial, into t, the number of particles. We have the integral over our density field. And then from exponentiating the delta function, we have our integral over its conjugate field W. Then in the exponential now, we have, so still minus beta u naught, care about that too much. And then I'm going to write out the beta u1 term just to make it clear that this is u0 over 2 r rho of r squared. And this is not rho hat anymore, right? So we've gotten rid of the particle density from this. This is now a continuous thing that we can work with. And then all of this is still inside this double integral. So then now we have, from the exponential term, we have two factors involving W. One where W multiplies the continuous field, and one where W multiplies the particle density. All right, so then we can write the continuous part first. So it's integral dr W of r rho of r. And now for the part where we have the particle density, we need to not forget that we still have the integral over their coordinates. We haven't gotten rid of that yet. But the only place that they're showing up now is all the way over here on the right in this last term. Actually, wait, I screwed this up. Sorry, the minus beta u0 has particle coordinates in it. Sorry. So that needs to be inside this integral. So it's e to the minus beta u0, because that's the bonded stuff that has to be inside the particle coordinates. And then times e to the minus I dr W of r rho hat of r. And that finally closes our partition function. Just to kind of highlight the main key features of this thing is that this is not rho hat of r, right? So it doesn't have the particle coordinates buried in it. That's the sort of key thing here. And the other important bit is that hopefully you might recognize that this is basically what we had every time we did the Hubbard-Stratanovich transformation before we turned all the particle stuff into n log q. Right, so this is now, since we only have a single factor of rho hat here, it's just each molecule independently interacting with a fixed field W. Right, and then this has the bonding information for all of the molecules. Right, so then this is the term that just simply becomes VQ to the IW, all raised to the n. Yeah, well, yeah, of course. Oh, sorry, that should be in total, of course, yeah. Yeah. The prefactor here should also probably change because of the self, yeah. Yeah. We use this property of the delta function, that since we're restraining it to be equal everywhere through that delta function, where we have an f of rho hat, we can replace it with f of rho. And so then our f here is e to the minus whatever density squared. And we had that f of was of rho hat, and now it's f of rho. Yeah, it's the identity of like what's being enforced by the delta function. Yeah. Any other questions on this? Realize I feel like I'm moving very quickly here, but. All right, well. And then what about this? Does this look familiar enough that we can truck along without going through it in detail? I hope. If you go back to the notes from when we first did polymers in the field theory, like you should hopefully see a term that looks exactly like this. And we turned it into this thing. And then, of course, the last thing that we will do is say that this is v to the n, then e to the n log q. And that gives us everything we need to define the field theory. All right, so now we have a partition function that is, just call it Z2 n factorial v to the n. And this v to the n, little n, comes from the definition of the molecular partition function. Then we have integral over the density field, integral over the potential field, and e to the minus h. And this has a functional dependence on rho and w. And let's write out what h is, just for completeness. So it's u0 over 2 r rho of r squared minus I integral dr w of r rho of r. And again, like none of these have the hats on them, so all the particle densities are gone. Then we have minus n log q of iw. And this has the exact same form as it did before, right? It's just, all of this is just another way of deriving a field theory that we can attack. And for a model like this, where we only have like a quadratic interaction, you could in principle take the integral over the density fields and turn it into just the one field model like we had before. right? Where for the original thing that we did for the Edwards model for the homopolymer and an implicit solvent, we only had the field W. We didn't have uh, an explicit density field in the model. But this density explicit version does have a few advantages. So this is, I guess, the sort of language that's emerging to describe this, mostly from Glenn's group, is that this is the density explicit auxiliary field theory. So the notation that they use in his newest book is DEAF. And one of the advantages of this is that since we have an explicit expression for the density, when we want to compute things like moments of the density, we just have to compute moments of this field that we've introduced. And so that makes the derivations a little bit simpler. So explicit field for rho of R to compute things like the average of rho of R, the 2-point correlation function of the densities. And one of the other convenient aspects of this is that we're not as limited with the types of potentials that we can do with this, right? So like we don't necessarily have to have a functional inverse for our potential for this method to work. And so that has a lot of advantages. So it lets you think about putting more complicated functions in here. We're going to stick to simple ones just because, well, that's what we're going to do. But you can do things that are like proportional to density cubed, which you can't do if you're only doing Gaussian integrals to get this out of there. And the Edwards model canonically is only good for a homopolymer in an implicit but good solvent, so where U0 is positive. But if you use this flavor of the model, you can actually deal with U0 being negative. And so then you can describe things like polymer collapse in a bad solvent, stuff like this, or phase separation from a bad solvent. All right. And so the explicit form for the density field is one advantage. And the other one is the little bit more complex interactions. All right. Okay, so this is going to be the field theory that we work with, is this expression. And so the first thing, I guess what we'll do for the rest of today is work through getting an equation for the second moment of the density from this flavor of the field theory for the model that we've already seen, right? This is the model A, or the Edwards model that we talked about, maybe not last week, but the week before. Oh, this is the one that we did the week in homogeneity expansion. So it's again the same model. And so we can use a lot of that weak fluctuation stuff that we've already done and bring that to bear here. Okay, so right, so the thing that we want to compute is S of K for the Edwards model. And then what we will do next time is talk through how you go about doing this for the diblock copolymer, which is a lot of algebra that we will not go through in detail. And so the strategy that works really well for this is, so we've seen that like S of k is proportional to the second moment of the densities, right? And so what we need, we take the Fourier transform of both sides of that. What we really end up needing is that second moment in Fourier space. Right, so rho of k times rho of minus k. And the strategy and the steps that we're going to follow is to use a partial mean field approximation. So we're going to say that W of R, we're going to use this mean field equation. We're going to assume that the fluctuations of this W of R field are small. And this is going to let us relate W of R to this density field that we've introduced rho of R. And we'll be able to relate them at the general level, but we'll also be able to relate them using this weak inhomogeneity expansion. So using the weak inhomogeneity expansion. And so effectively, that's going to get W out of our partition function. And then we'll have a model that only depends on the explicit density field, rho. So then that'll let us compute this second moment. And this last step turns out to be fairly quick and easy. Right, so we'll compute this as the second moment of a Gaussian. All right, so this is where we're headed. Let me just delete it or erased all my equations that I probably should have left them. So recall the weak inhomogeneity expansion for the homopolymer, for the Gaussian homopolymer. Right, this is what we did, I guess it was a little over a week ago. We had that Q of IW. This was roughly W0 N minus squared E squared sum over K, the bifunction W of K, W of minus K. Hopefully you remember this from, maybe it's been a little bit, but when we did the weak inhomogeneity expansion, this was one of the sort of key results that we got at, where this G of K here is the Debye function, right? So it tells you about the form factor of a homopolymer. All right, so what we want to do is take dH by dW. So let me write out H again so that we have this handy. This is U naught over 2. This and Q. So let's get at this mean field equation. That's the first kind of key thing that we need. So d by dw So when we take the variation of this guy with respect to W of R, the first term that we get is just simply minus I rho of R. It's just the density from the integral of the product. And then this thing, right? So this, if you recall, we had D minus N log Q by D by W. This was the thing that we called our density operator. So the row with the tilde on it. Again, this is going back a little bit, but hopefully this is not too unfamiliar. So when we take the derivative of, so we'll have, so that ends up being plus I rho tilde of R W. It's meant to be a semicolon. Yeah. It's the notation that I sometimes use to denote like the vector or scalar dependence from a functional dependence. And so when I don't think we actually showed did we show the weak and homogeneity expansion for this guy? I don't remember if we did or not, but we need to take the log of this thing, of n times log of this guy. Assume that this term is small, so we can expand the log a bit. Actually, no, we don't. Actually, we don't even need to do that. What we can show is that all of this becomes, so when we're taking d by dw of this q, right, we're taking the functional derivative with respect to w is the kind of key thing that's going into this. It's going to kill off one of the w's, right? And it's going to leave behind the product of g times the field w. And I'm just going to give the form that it turns out to be, that this product of I times rho tilde becomes plus rho naught, the constant, so the average density, times n gk stuff k. So this whole term becomes minus I, wait. Oh, yeah, sorry. Yeah, that's the expression that we need. Sorry, I'm doing some really silly things with my notation here. Let me clean this up a little bit. So this should be dH by dwk minus I k. Yeah. Yeah. So what I've done in going from here to here is take the Fourier transform of both sides and use the weak and homogeneity expansion for this guy. So we use this approximation for it. Okay. Now we use the mean field part of this. So we set this thing to 0. And so then that lets us just algebraically solve for the relationship between W and rho. So we put I times rho on the other side and divide through by rho naught and GK. I, rho K, rho naught, chain length, and the bifunction. Okay. Sorry for the bit of confusion on my math here. Any questions about this? I realize it's getting a little dicey. But now that we have this relationship, though, we can go back to our expression for H and plug in and get rid of W everywhere so that we only have the densities. Right? Right, so we will have our H is going to be U naught over. So the other thing that I'm going to need to do is use some of those Fourier transform tricks that we used last time, where we wrote these integrals as like integral over space, rho of K times rho of minus K. Like that kind of stuff is going to show up again. So if U naught over 2V, sum over K, rho of K, rho of minus K. All right, so that's the term that comes from this. So we haven't done anything with that one. Now we plug in for W of K in here. We will have minus I 1 over V sum over K. And again, we're going to plug in like the product of W of R and rho of R becomes W of K and rho of minus K. Or you can play with the minus sign, it can go wherever. But so then we plug in for W of K using the mean field equation we have. All right, so we will have I rho K over n GK in GK. Then this is times rho of minus K. All right, so that comes from the I integral W times rho. Then from the n log Q term, there's a couple of things. So there's this constant that'll show up that we're not going to care about, but we'll write it down for now. In W0 is that mean field constant. And then we'll have plus, again, we're going to plug in for W of K and W of minus K with this guy. All right. So rho naught n over 2V, that comes from the constant prefactors that were there anyway. Sum over K, I over naught n GK rho of K times, that's from the first factor of W, so W of K, then I rho naught n GK rho of minus K. And then we still have the other factor of the Debye function multiplying these guys, right? So times GK. Right, so let's do a little house cleaning on this. Okay, so there's not a lot that we can do with this first term, right? It's just rho of k times rho minus k with a constant out front. That's fine. We can leave that alone. The next one, and again, this term is the one that comes from plugging in for this guy and writing it in Fourier space. We have a product of two i's, so we can cancel those out and make that a plus. So those go away. This thing is just a constant that you can either lump it into the prefactor of the partition function or think of it as a shift in the free energy. Whatever, it's gone. We're not going to deal with it. So we don't need to worry about that. And then in the last one, let me see, we have two i's, damn it, multiplying each other. And so those will give us a minus sign out front. And then one of the Debye functions cancels, and one of the other denominators cancels with the prefactor. Okay. So that lets us simplify things to a pretty manageable state. All right, so what's going to happen here? Let me see. Let me make one more thing explicit. So I then take this whole expression with all of these cancellations and everything, right? This is going to become equal to minus, the i's are gone, it's 1 over 2v, sum over k. We'll have rho k, rho minus k, and then it's just divided by rho naught in gk. And so then this term that comes from the n log q is the same as the one that we had above from the w times rho, just with a factor of a half. And seeing this combination of terms is like the first sign that you're doing your algebra correctly. So when we combine those two terms, we're going to go from kind of a 4 messy term expansion to something that only has 2. And so it's getting to be a little bit more manageable. So now we have our effective Hamiltonian that's still u naught over 2v sum over k, rho minus k. And then what comes out of the second term, so we have plus 1 over v, then minus a half, 1 over v times a half. So we end up with plus 1 over 2v sum over k, 1 over n rho naught gk rho minus k. All right, and we are now almost done. So now we have our H, effective Hamiltonian. The whole thing becomes, so where did it go? 1 over 2v, and now we'll just collect all the prefactors as just a simple k-dependent constant. So it's gamma k, because we have rho k and rho minus k in both terms. We can just combine the sums. Just call that a weight vector dependent prefactor, rho of k, rho of minus k. And we've defined this thing to be u0 plus 1 over rho naught in gk. Right. Now we're actually almost done. So finally, once we've done this approximation, our partition function becomes, it simplifies all the way down to some prefactor that I'll just call Z3. And I'm just going to throw all the ideal gas and everything in there just to not think about it, because that's not the part that's actually tricky to deal with. Then e to the minus 1 over 2v sum over k, gamma k, rho minus k. All right, so the mean field approximation is what got rid of our integral over w. And then we use the weak homogeneity expansion along with that mean field approximation to relate the densities to the fields, right? And that's what let us explicitly eliminate them from the equations. All right, but now this is back to the form of a Gaussian integral like we talked about last time. Right, so when we came up with expressions for the free energy, we just explicitly integrated this thing out. The thing that we actually want now is just rho of k, rho of minus k, because this is the thing that's related to the structure factor itself. And so then this just simply becomes the functional integral k minus k minus h. It's a ratio Gaussians. So it's the second moment of a Gaussian divided by the integral of the Gaussian. And so since this is just a ratio of, or this is just the second moment of a Gaussian, what comes out of this is that this average, this rho of k, rho of minus k, just comes out to be 1 over our gamma. So in other words, our static structure factor, S of k, is just 1 over gamma, so u naught plus 1 over rho naught in gk. And if we play our usual tricks of multiplying this by a complicated version of 1, try to cancel stuff out in the denominator, and we just get the k-dependent term in the numerator. This is rho naught in gk over naught rho naught in gk plus 1. And that's it. So this is, for a polymer in solution, this is as long as it's a good solvent, this is the expression that has been like tried and true and beaten to death for the structure factor of the polymer in solution. And so whereas G of K itself is mostly like a form factor of an isolated chain, this has some collective information in it about all of the chains. And that's why it comes out to be just different from the Debye function. And it also, of course, has the interaction term in there from u naught. All right. And so again, sort of the key steps really are using this other Fourier, this other particle to field transformation technique, this Fadeev-Popov method. So you use these delta functions, which in some ways is easier, but you end up with kind of longer equations, but they're a little bit more intuitive, I think, to work with. And then you do a mean field approximation on the potential field W and the weak homogeneity expansion to relate W to rho. And those things are the ingredients that you need to be able to put all of this together. And the main thing that changes when we go to die blocks, which we will work through next time, is that there you have two species that you have to work with, right? There's an A block and a B block. So you can't use a single delta function to eliminate them. You have to introduce a delta function to get rid of all of the A components and a delta function to get rid of all of the B components. So then you have a two density and two field model to work with. And that just makes the algebra considerably messier. But the idea and the steps are exactly the same. And so we will talk through that a bit next time. And like the setup is less than a page of my notes. And then the algebra, you can see, is many pages of my notes, and we will not go through it. I will send the PDFs, and if you're that interested in the details, you're welcome to go through it. But we will at least get to write down the structure factor for this. And if I remember, I'll write up some Python stuff to plot these functions so that we can see what they look like, because I think that would be handy. Yeah, all right. So I think that's a decent stopping point for today. So we'll definitely be able to finish the die block next time. I don't know if we want to have another meeting next Thursday. It's kind of up to y'all. We could talk through a bit of like numerical methods for doing these things without like analytic approaches. We could talk through that a little bit if y'all are interested. All right, maybe I'll try to put some notes together for that for next Thursday. And then that'll probably be it. All right, well, we will call it there for today. We will resume on Tuesday. We'll do the die blocks. And then on Thursday, we'll talk a little bit about mean field approximations and doing it numerically without weak and homogeneity stuff. And yeah, that'll be it. Cool. All right. Well, have a good weekend, and I will see you all next week.